So let's do first a brief review of what we have gone through. So first, the definition of combined momentum flux tensor, and some of them you have as an exercise to compute in your homework. System is a little slow in responding to my changes. Okay. And we have basically contributions to overall, or what we call combined stress. Here I'm writing it as a tensor simply because I want to shorten the writing. Has molecular components and what we call convective components. So contributions to the molecular part are those that are hydrostatic. That's thermodynamic pressure contribution that is there regardless of whether the fluid is moving or not. And it acts the same on all sides, always normal to whatever surface we have. So that's why you only these normal components, they're acting orthogonally to whatever side, coordinate side you're looking. Here we go. He is walking. Excellent. Congratulations. It doesn't feel very celebratory right now. All right. So normal components are the ones that are non-zero, and shear components are zero for the hydrostatic part. Then we have the viscous stress, okay? And viscous, so each of these components, this is basically X component, X momentum transfer across X plane, and this one here is Y momentum transfer across Z plane. So we have to look at all of the X, Y, Z components of the momentum transfer across X, Y, Z planes. That's why we have a full tensor. And then we have the convective part. So this is dynamic that really exists only if I have spatial differences in velocity. Okay? And then here I have the convective component. That's simply stuff that flows in through a boundary. So if I have an X plane, okay, only stuff that is orthogonal to that X plane is coming in. Okay, so basically I have here rho v x v y v z. This is my old rho v is my momentum, and what flows in through the X plane is that momentum times Vx. That's what's in this column here. And then here we have that same rho Vx, Vy, Vz, rho V multiplied by Vy. That's what flows in through across Y plane and then across the Z plane. So again, I have to have a tensor describing all of these. So it's component-wise, it's actually easy then to write this down. It's really rho Vi Vj, where Ij is my combination that I'm looking at. So this is how to write these down for each spot right here, right? Each Ij position, where Ij can be any plane. Now, this description technically is valid in any coordinate system. Here I'm writing it as an XYZ coordinate system, but it could be cylindrical or spherical. Okay. Now, what is delta Ij again? This is shorthand notation. Identity matrix elements. So they're going to be 1 if I is equal to J and 0 otherwise. Okay, that's also called Kronecker delta. So I have again pressure component, P times delta Ij, viscous component, tau Ij, and convective component, stuff that literally flows into my control volume, rho Vi Vj. Excellent. That's my combined momentum flux tensor. I haven't told you anything about the nature of the fluid yet. So in this particular formulation, this is true for Newtonian and non-Newtonian. It's how do you describe this tau Ij that differentiates which fluid I'm talking about. And for Newtonian fluid, that's where our relationship between shear stresses and the velocity gradient is linear. That's the simple one. That generalized relationship is this shear stress is I take the Jacobian of my velocity plus Jacobian transposed. So this is all of the partial derivatives of my velocity. Velocity has x, y, z components. So all partial derivatives in x, y, z directions are filling in a matrix as well, right? And if I'm in a different coordinate system, it's not x, y, z, but it could be r, phi, and theta, for instance. Okay? So these are different coordinate. So this is a tensor, this is a tensor, and I have only a constant mu here, which makes this a Newtonian fluid. Okay? And I also have to add this part, which will often simply vanish. So when I have incompressible fluid, divergence is 0. And we will get to proving that. But if I have a constant density, incompressible fluid, water, this will be 0. So we will simply ignore this part. But more generally, when I have compressible fluid, I do have to account for changes or compression, local compression or expansion of that fluid, because that affects my viscous stresses as well. Okay? All right. We've survived through definitions. And then we said, okay, now let's actually solve something with this. So we have introduced general shell balances. Whenever I mean shell, I'm defining a little small piece of fluid, okay, that is aligned with my coordinate system. So I'm looking at the little box in my coordinate system. So it's a box in Cartesian coordinate system. In cylindrical is quite literally a shell, right? A little like annulus. And I'm going to basically look at what comes in terms of momentum. Momentum is flux of stuff. Flux, it's stuff flowing, and stuff could be anything. In this case, we're looking at momentum, rho v. But I could also have, in diffusion, we're going to look at the literally particles and like things diffusing through, right? So it could be mass flux. It could be momentum flux. It could be heat flux. Okay? Flux, I understand, is something that is divided by area. And since it's flux, it's in time, okay, per time. So basically per area per time. So to actually look into what is coming into any volume, I'll have to sum up everything that is going across an area, either inside or outside, in most general case. And stuff that is going inside is always stuff that is orthogonal to an area element. Okay? Now, if I have simple boxes, these things are relatively simple to put together. And that's what we're going to do in most of our cases. So we're going to simply look at our rate of momentum change or accumulation within that element is momentum that comes in minus momentum that comes out. And external forces such as gravity could change momentum as well, okay, because they can change velocities and therefore their differences. So they're going to affect momentum, but they act on a volume. They don't act through the boundaries or through the areas, right? So essentially, I will have sort of a body. This is the body part, and this is stuff that is coming in through the boundaries. Okay? So of that little shell, so here I'm going to have sort of a volumetric contribution to the change in momentum, and I sum those up. If I have steady state, this will be 0 because I'm not going to have accumulation, right? And then we're going to shrink that element and essentially obtain a differential equation. We will need boundary conditions that we're going to mention to actually solve it. So this is what we started working with for a thin film going down an inclined plate. I have beta as an angle here of the plate. It's really a very low angle. Okay? So I'm assuming that my fluid is very ordinary. It's a laminar flow of Newtonian fluid, so it's described with a simple viscosity. It's steady state, so I have I waited for it to stabilize in time. I don't have any or consider any disturbances that I would have in the lab by entering and exiting, so I'm somewhere in the middle of the flow where it's well established. Okay? So, and nothing changes into the screen. Okay? So I have delta is now my film thickness, and it's considered small. Okay? And I'm assuming, so I'm first put together a coordinate system. That coordinate system should be parallel to the boundaries, solid boundaries, as much as I can. So here I'm going to define the Cartesian coordinate system where z is parallel to this inclined plate and x is orthogonal to it. And y I basically right now disregard. But it's going into the plane and everything is repeated in y direction. Whoa. So this z are my only velocities going down. I'm assuming that there are no x velocities. So basically my vx is 0 and my vz is just a function of x. That's a simplifying assumption. Okay? I'm also ignoring any kind of acceleration down this plate. So I'm not assuming that vz will change as I go down the plate because the plate is barely inclined. Okay? That's a simplification. So it's sort of like a first order accuracy if you think about it. Okay? And then I'm going to really look into only z momentum transfer into this cell. So there's a little small shell parallel in this coordinate system, parallel to both of these axes. And when I blow it up, my shell will be, so now I need notation. It will go from z to z plus delta x, z, and from x to x plus delta x. So this is my little box. Now I have z and x, so my combined momentum components that could be taken into account here are phi xx, phi xz, phi zx, and phi zz. Okay? Now, phi xx is x momentum across x plane. So for the moment, I'm not going to regard it. I'm going to balance z momentum because I'm looking for z velocity distribution. Right? But I could balance x momentum as well. So I'm going to look into this phi xz, which is z momentum across x plane, and phi zz, which is z momentum transfer across z plane. So z, z, across x and z. Where are they here in this box? So here I have an x plane. So this is going to denote a transfer of z momentum across x plane. Yes? And I have same here as just in a different location. This one I refer to as phi xz and then sort of like a vertical line evaluated at x. So x is constant here. Okay? And this one is the same phi xz evaluated at x plus delta x. So this is just a shorthand notation. So I don't write phi xz at x plus delta x comma z. Right? And then I will do the same for phi zz. So here coming in, I have phi zz evaluated at z. And here coming out, I have phi zz evaluated at z plus delta z. So what's coming in minus what's coming out plus whatever external forces due to my volume element has to be equal to 0. That's my balance. So that's my shell balance. Coming in, phi xz at x, this is per area, so I have to multiply it by area. And my area is here delta z times whatever is going into the y plane. You can write it down or not. I wrote it down simply so that our dimensions are correct because I have to multiply by area. But technically I can just ignore this w, this width into the plane all along. Okay? So this is my phi xz at x times delta z times w. And what's coming out on the other side is phi xz at x plus delta x delta z w. So this is in minus out in this direction. And then phi zz evaluated at z times area, which is now delta x times w, minus phi zz at z plus delta z, that's right here, times this area here, right? So flux I have to either integrate over area, or if it's constant on that chunk, I can just multiply it by area. Is that physically? Right? Okay, so this is in minus out, and then I just have a z component of gravity acting on this volume here, and that has to be equal to 0. So all of this is just the z coordinate, okay? Because I really considered only xz and zz. So there's just z coordinate of what's otherwise a vector equation. Okay. So when we divide this entire equation by the volume of the element, this part here will be essentially divided by delta x, because these two things cancel. And this part here will be divided by delta z, because these two things cancel. So I will get something looking like this. And then I remind myself that partial derivatives, their definition in general, for some general function f, is limit when I shrink delta x to 0, for instance, of x plus delta x minus f of xy divided. This is my f evaluated at x plus delta x and f evaluated at x. So basically, I can rewrite this by putting minus up here. This is again shorthand notation. This is my phi xz at x plus delta x minus phi xz at x. And this is just writing it short way, divided by delta x. And this is minus the similar phi z, z plus delta z, that's this one here. Plus, I have just a constant here. G cosine beta is my z component of g. Yes? In that coordinate system. Is equal to 0. And then I take the limit when both delta, I shrink this shell to a point, when delta x and delta z go to 0. And that gives me partial derivatives of these things. This is how I in general obtain differential equations that rule from any kind of balances of anything. In this case, we're balancing momentum. So I'm going to get partial x of phi xz minus partial z phi zz plus rho gz cosine beta is equal to 0. Questions? This is basically a review, not so fast, but a review of what we've done last time. But this is important. I want to review this once again because this is basically the fundamental steps in putting together a momentum balance. This is combined momentum. I haven't specified anything about the fluid yet. Okay? So we are now going to continue this. So this is combined. This is combined momentum balance, Z momentum balance for any fluid. I haven't described my phi yet, so there's nothing specific to the fluid. This is pretty much true for any fluid, any thin film going down the plane in that coordinate system that I described. Okay. Now let's actually write down what phi xz and phi zz are. Do we remember? Phi xz, there's a pressure / hydrostatic plus viscous stress plus convective. Okay, 3 contributions. P delta xz plus tau xz plus convective is rho pi vj for general ij, so it's vx vz. Yeah? What is delta xz? This is that Kronecker delta, it's component of identity matrix. It's a 0. Excellent. Okay. Now I will apply assumption that this is Newtonian fluid. Okay. I have big fingers that touch things that touch. Newtonian. And for Newtonian fluid, tau tau xz is going to be equal to what? Can you find out the formula? Yes, so I have that additional part that depends on the divergence of V, and we are assuming incompressible fluid. And for incompressible, divergence of V is 0 if I have constant. Incompressible with constant density. We're going to get to proving that, but for now, just take it as a definition. So rho V is equal to 0 for incompressible fluid with constant rho. Okay? And then what did I assume about our velocities? What is my Vx? That's that into the plate. It's a 0. Excellent. Another one 0. So that's by assumption. So the only thing I have here is really tau xz. Okay. Now, what is my phi z? It's p delta zz. Delta zz is now a 1, right? Because I have a normal component plus tau zz plus rho vz, which is vz squared, really. So what is my tau zz by definition? Not a 0. Minus mu. Well, will be 0, but by definition is this. Right? And then the divergence part that is 0 anyway, so I'm not going to write it down. So my Vz, by definition, or by assumption, not by definition, is a function of x, right? And therefore this partial derivative with respect to z is a 0. Yes? This disappears. Plus rho Vz squared. Vz is Vz of x squared, so I'm just writing it as is. Now, is this function phi zz? So I have rho Vz squared, which is technically a function of x by assumption. And by the extension, my pressure, I don't expect it to change in x direction. I don't expect it to change in z direction, otherwise I would have acceleration in z direction, right? So my pressure is technically a function of x as well, right? So this is really p of x plus rho vz squared of x. So now I'm going to put it into my equation here. So I have minus partial x of phi z minus partial z of phi z plus rho g cosine beta. So I have now my main equation gives me minus partial x of tau xz. I'm still going to write it as a shorthand side tau xz. minus partial z of phi z, which is a p of x plus rho vz square of x plus rho g cosine beta is equal to 0. So I have a partial derivative with respect to z of something that depends on x. Anybody recognize the pun here about biting the
You all are too young. Okay. Queen. I, when I was in high school, queen is queen was so I
still think it's a deal. Anyway, so what I really have is that minus x derivative in x direction of tau xz is equal minus rho g cosine beta. So my partial tau xz partial x is equal to rho g cosine beta. I still haven't actually applied the assumption that this is a. You see what I did here? I just kept it as tau xz. Could be any form, really. Now, this is a partial differential equation. It's really, I'm often going to put this general partial x, but since I did have an assumption of things depending on the x direction, this is d tau xz dx. Because I really have a function of one variable in here. So I'm going to interchangeably use these two, so just get used to it, because this is a partial derivative with respect to x, but everything will really depend on just x. If I had that z dependence, I would have acceleration in z, and I killed that to begin with. So this rho is constant, g is constant, beta is constant. This is a constant. The way differential equations go, this should be really simple to solve. What is it? Tau xz is rho g cosine theta times x plus some constant c1. I'm just going to write it as c1. And obviously, it's a function of x in this problem. Yes? You can't get simpler equation than this. Even if you knew nothing about differential equations or remembered nothing, you could remember that if I have a derivative of something constant, well, the general solution is a linear function. Now, to solve any equation, so this is general. No assumption on the fluid put in here. So now we need boundary conditions for this C1, right? I haven't really mentioned much about boundary conditions yet. And I'm going to refer to boundary conditions as B. So this is my sketch that I actually know that I have in this. So I have, this is my plate is on the bottom. And then on the top, I have this air and some sort of liquid going down, right? A very common assumption for slow velocities, which in this case we have, is that shear stress on air-liquid interface is 0. This comes from the fact that I'm assuming I have to have continuity of shear stresses across any boundary. So On one side, I have air, and if you think about it, it's sort of like mu of air times some derivative in velocity, right? And on the other side, I have mu of liquid times derivative of velocity. Typically, viscosity of air or gas is at least an order of magnitude lower than that of liquid. Yes? So for air, it's close to zero compared to any liquid. So on the other side, I have something, I have continuity across this boundary, and I have something that is very small viscosity. And that viscosity basically makes my shear stress zero, a very low viscosity. Because I don't assume I have very large gradients in velocity in this application. There could be, can you imagine some air-water interface where my gradients in velocity are large and my velocities are large? Outside of petroleum engineering, but in general in nature? I could have like storm, those velocities are large, right? And then when I'm shearing the top of the fluid, maybe the viscosity of air is close to zero, but those gradients in velocity are large, so I can't assume that my shear stress is zero because it's multiplication of gradients. And okay, so let's go back to this. So I need BC, so a very common one. I'm going to call it BC1, is that shear stress in liquid air interface is zero. And this is good for when my velocities are small. And that's basically where my coordinate system started. So my tau xz of 0 is a 0. That's rho g cosine beta times 0 plus c1. So what is my c1? So really what I have is that my tau xz x is rho g cosine beta times x. So physically, what I have in this particular situation is that I have zero shear stress at my air interface, and it just linearly grows in x direction until it meets the solid surface. Yes? And it's maximum on the solid surface, where liquid and solid are going against each other. Right? So my maximum tau xz is tau xz at delta, and that's rho g cosine beta delta. And it's linear between 0 and delta, yes? This is a very common physical insight. In terms of absolute values, my shear stresses are maximized on solid surfaces, and often zero. They're minimized where the velocity is maximum, sometimes like in the middle of the profile, or here where I have an open surface to the air, they're minimized at the interface with air. Okay? If I did not have contact with air, they would be minimized somewhere in the middle, like in those parallel plates, it's going to be minimized in the middle where the velocity is maximum. Okay? That's how shear stresses always work. Excellent. So this is shear stress really regardless of the fluid. Yeah? So I could have Bingham, I could have whatever. This is my shear stress. It's really how velocity. Now, so I really want to get the velocity distribution. So for velocity distribution, now I apply assumption that this is Newtonian fluid. Okay? For Newtonian fluid, my tau xz, we already did that, is minus mu dvz dx. is equal to rho g cosine beta x. So this is my tau xc, right? And since my Vz is just function of 1, we need a whole lot of Blasius this morning. The round of calls is making, I'm going through my 4th one this season. I'm not amused anymore. Way worse than any. So this is really dVz dx. So d is for single variable function, delta is for multivariable situation. But in this case, it's interchangeable. So that's equal to, when I put minus mu on the other side, minus rho g cosine beta over mu x. So when I integrate this, it's a little harder than the previous one, but not too hard. I have linear function on the right-hand side, so integral will be x squared something, right? Integral of x, generally speaking, is x squared over 2. Yes? Plus a constant again. So my Vz of x is minus rho g cosine beta over mu, x squared over 2, plus I'm going to call this constant C2. Now I need another boundary condition to actually solve this. And this is going to be our second most commonly used, actually probably the most commonly used. It's so-called no slip at the solid surface, which basically says that the fluid and the solid at their contact have the same velocity. Now, if that solid is static, that means that my velocity is 0. If the solid is moving, then the fluid is moving with the, let's say that I'm pulling a piece of equipment, then the velocity is matching that. Okay? The fluid velocity is matching that. Okie dokie. Well, so we're going to apply that BC2. Assume, it is an assumption, no slip for BZ at x is equal to delta, so that's solid surface. And since my solid surface is not moving, then my Vz of delta is 0. Delta is that film thickness, if you remember. So then I have, in the above equation, I have 0 on the other side, so my C2 is the same expression here for just with x is equal to delta. So my C2 has to be rho g cosine beta divided by mu delta squared over 2. And that gives me Vz of x, which is rho g cosine beta over 2 mu delta squared minus x. Yep, there we go. This is what we call a parabolic profile. Now, my shear stress was minimum at the air-liquid interface and maximum at the solid. Velocity is opposite. It's 0 at the solid because solid ain't moving, and that's causing all of the shear stresses, right? And it's maximum where my x is 0, right? And that's near that, right? So they're kind of always in reverse. And I have basically this parabolic profile is shown here. Okay? So as a review, we assumed very thin of thickness delta, much less than the length in Z or any width that is going into the plane, very thin film. My y direction is ignored. It's essentially repeated, so I don't need to solve for it. So I have a two-dimensional problem. I further align my coordinate system with this solid plate. My z is moving down, x is into the orthogonal to the plate, and I'm assuming that my vz velocities are really just function. I have this layered fluid and really just function of x, and the other two velocities are zero. Then my pressure has to kind of behave the same for both z and pressure. I don't assume any change in z direction, no acceleration. I'm really just ignoring it. It's there, but it's small. It's probably an order of magnitude smaller. And if it's not, well, then I solved the wrong problem. Okay. And I'm open to air on top. So the next thing, whoops, I have to apply boundary conditions. There's no slip on the solid wall, so I'm moving with the velocity of the wall. And shear stresses are zero on air-liquid boundary, which is okay assumptions for small velocity changes. And when we apply Z momentum balance, we had a very general formula that we derived by looking at the shell. We get this velocity distribution, which is this parabolic profile. So again, shear stress is minimized at the air-liquid interface, maximized at the solid. Velocity is the opposite. It's minimum at the solid, which is zero in this case, and maximized at the air-liquid interface. This could be slightly different if my solid was actually moving. So things are relative to the solid. Okay? And I will ask you on your own in your next homework to actually just balance x momentum and see what you get. Since we already solved for Vz of x and we assumed Vx is zero, we're not going to get Vx. It's a zero, right? But you're going to get a function for P of x out of it. So pressure is a linear, really, function of x. So it's a very simple solution, but it's a practice in applying the z momentum, x moment, or practice in momentum balance. Now, we can admire this parabolic profile, but we really want some engineering quantities of interest. Their maximum velocity, what is the volumetric flow rate, what is the average velocity, because those are the typically things that we can measure and compare to what we measure in the lab. And also, what is the Reynolds number for the flow, so we can actually calculate it and see that we indeed have a laminar flow regime. So those are listed here. Maximum velocity is easy. It's the one at zero. We already looked at that. Volumetric flux, you basically aggregate everything that is going through a certain surface. And in this case, I'm going to aggregate means integrate over an area. So here I'm going to integrate with respect to dx and dy, which is volumetrically into the plane. Okay? For assuming that that plane has width into the y, it has width w. Okay? So I'm going to integrate, if this is my slope, okay, going down, I'm going to integrate across this area that is in z direction and also down z direction and y direction into the plane. Yes? To collect volumetric flux through that area. And that is the integral of Vz of x that is going orthogonal to that z plane, dx dy. And when you do that calculation, which is also going to be your homework, you get the expression that is shown. Average velocity is basically taking volumetric flux, dividing it by the area. This is a general formula. So you can just divide this by W delta. And my Reynolds number for this flow is defined as 4 delta average Vz rho divided by mu. So if you remember, we need some sort of measure of the geometry for this fluid, and delta is the main confining this thickness of the film. Average velocity is a common thing to take, rho and mu. 4 is there for historical reasons. And often there will be somebody or whoever was the starting researcher in the field starting using it for one reason or another. and that's what sticks. So for every different geometry, you will typically have slightly different coefficient here. Maybe there's a 4, maybe there's none. Maybe there's just a radius, maybe there's just a diameter of the sphere if we have spheres and so forth. Okay, so that's something to be used to. Here, we should have Reynolds slightly less than 20 for this proper laminar flow regime. Okay, so I'm going to let you compute this volumetric flux and average velocity as part of the homework to actually integrate this. All right? All right. We will continue on Wednesday with flow through a tube.